Hi everyone! Today we're going to talk about slope fields. Essentially what slope fields are, it's a way to visualize the slopes of a particular curve. So what we're going to have here is, rather than giving you a function and saying, let's take the derivative, we're going to start off with a function whose derivative you know, and we're going to try to piece together what that function should be by drawing out a picture. So let's say I give you an equation like this one, dy dx is equal to y. Anytime you have an equation where there's a derivative involved, we'll call this a differential equation. We'll occasionally abbreviate differential equation by saying diff-eq, but I'll try to say differential equation as much as I can. Now, here's the particular equation I'm concerned about. Dy dx is equal to y, and maybe you can guess some functions that would work here, but maybe you can't. Regardless, we're going to sketch it out and show what functions might have to be. So what we're going to do here is we're going to draw our coordinate plane. And now on the coordinate plane, we're going to put a bunch of points. So let's just go 3 in every direction for starts. 1, 2, and 3. And now I'll put just nice dots, 1, 2, 3, 1, 2, 3, 1, 2, 3, for each point that's actually has integer coordinates on this plane. 1, 2, 3, 1, 2, 3, 1, 2, 3. Alright, and maybe this seems a little tedious, but you'll see in a moment why it's particularly useful. So we have all of these points. And now what I'm going to do is, at each point, I'm going to draw a small line segment that has the slope dictated by this equation. Now, why would I do this? Well, remember, this is telling me the slope of the tangent line, no matter where you are, is just y. So if I sketch in these mini tangent lines, what I can do is I can try to draw a picture of a function that hits all of the tangent lines, and therefore I'll be able to say, oh look, it looks like this. Occasionally we won't be able to solve differential equations, but we can still visualize them using this method. What we'll do for a couple of examples here is I'll give you some that we could solve, but we'll choose to solve them this way. That way we have more than one way to check our work. So if dy dx is equal to y, what does that mean? Well, any of these bottom points here, they all have y-coordinate -3. Since the derivative does not depend at all on the x value, this whole horizontal line has to have a very steep and negative slope right there. Okay? As we move up, this line here has a y-coordinate of -2, so still quite steep and still negative, but maybe not quite as steep as we were at -3. And then we'll have, oh look, y is -1, so now it's just even less steep and completely constant slopes here. Right on the x-axis, we have a slope of 0. Once we move up, we get y is equal to 1 as our slope. We get y is equal to 2 as our slope. And we get y is equal to 3 as our slope. Great. And so now comes the time where we'll pick a place to start and then kind of sketch what our curve should look like. So let's pick, oh, I don't know, right here as our starting point. We need to draw a curve that's tangent right at this point. No problem. So there are lots of curves that do this, but we also want to know that as we move up, we should be getting steeper, and as we move to the left, we should be getting less steep here. As we move down, we should be getting less steep. So as I move to the right, I need to get steeper and steeper and steeper and steeper. And as I move to the left, I need to get shallower and shallower and shallower and shallower. Great. Now, that was one particular point that we happened to start at. What if we started somewhere else? What if we started here? Well then, my curve would look like this guy. And maybe you can tell that these functions are related to each other. Turns out no matter where you want to start, you'll always get a similar looking function. These functions are all exponential functions. And that might make sense to us because, well, our favorite exponential function we know is e to the x, and its derivative just so happens to also be e to the x. So, hey look, this is a function whose derivative is itself, and that's what the original differential equation was telling us. Okay. Still, might be a little tricky, so we'll do one more example like this, and then we'll do a slightly different example. Let's do that here. All right, so next equation we have dy dx is equal to negative x over y. Again, a differential equation to start with. And again, we'll start using the same method here. We'll plot all of our points. So we'll go 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, and we'll just stick all of our points right there. I know this can be a little annoying to do every time, but as we get better and better and better at it, we'll need to do it less and less and less. We're just doing it so that we can visualize the slopes. But once we get more comfortable, we can see, oh, as x increases, the slope's increasing and becoming more negative. As y increases, the slope is decreasing. Things like this, and then we can kind of sketch for ourselves. But let's see here. Let's just fill in our grid. So if x is 1, let's fill that out. So when x is 1, if y is negative 3, I'll get 1 over negative 3, which is 1/3. So a very slight slope, slight positive. If y is negative 2 when x is 1, I'll get negative 1/2. So again, very slight and positive. If y is negative 1 when x is 1, I'll get a slope of 1. Great. If y is 0, I get negative 1 over 0, which is undefined as a slope. That means a vertical tangent line. Right up here, I get 1, 1, so that's negative 1. I get negative 1/2 and negative 1/3. And I'll do this similarly for every other point. So you might notice that if x is equal to y, my slope will be negative 1 every single time. So x is equal to y here and here, and here and here and here. Slope's always negative 1. You might also notice that when x is equal to negative y, our slope is always 1. So that happens here and here and here and here and here. And maybe now we're starting to see what our picture might look like. Anytime y is equal to 0, we'll get a vertical tangent line. Anytime x is equal to 0, we'll get a horizontal tangent line. And we could continue and fill out the rest of this, but let's see if we can try to draw it right now based on a given starting point. So we'll notice that if we started maybe here, well, we have to kind of look like this nice octagon type shape, except we're going to be a nice smooth curve. So we'll come around and we'll be a circle. And if we started further out, you should notice the same thing here, another nice looking circle. So no matter where you start, again, you're always going to be curving towards one of the axes and then back around in a circular shape. Now maybe the equation for a circle you also recall is x squared plus y squared is r squared, assuming we're centered at the origin, which we are in this case. And if we wanted to find dy dx, we could do that using some implicit differentiation, which we remember. 2y dy dx, that's the implicit part, and since r is a constant, that's going to be 0. Oops, that's not 2x squared. Solving this gets us dy dx is negative 2x divided by 2y, which is negative x over y. Hey look, that's exactly what we had here. Great. So again, our sketch matches what our algebra tells us, which is really, really good. We always want this to happen. And as we get more and more familiar, again, we learn some more techniques to figure this out. But for right now, sketching it's a great introduction for how to do that. Okay, but here's the last case, and this case might be even trickier than the previous ones. In this particular case, I'm going to start off with a slope field already drawn and ask to find the differential equation. So this one might be a little tougher, but we'll plow through it anyway. Here's the given picture that we're going to start with. Let's see here. I've been using these blue lines for the slopes, so let's do that. We have a nice horizontal slope of 0 here, whenever x is equal to 2. And then the slopes turn this way, positive, and then even more positive as we move along the x-axis. They're negative to the left of 2, and then even more negative as we move along the x-axis. So here's what we should notice from this graph. We notice that anytime we move vertically, the slopes don't change at all. Right? In this whole vertical line, the slopes are all 0. This vertical line, the slopes are all positive and small. Here they're all positive and larger. So what we should notice is when we change the y-coordinate, our slopes aren't changing. That means the derivative shouldn't depend on y at all. So what we'll do is keep that tucked away in our mind and now try to draw in some curves here that might make sense. So it looks like if I start on the left, I'm coming in real negative, I get less negative, I get to 0, I get positive, and then I get more positive. Maybe our curve looks something like that. And if I started somewhere else, say over here, I'd get the same picture, just maybe moved up slightly. And that's fine. We should notice that each time I get this nice looking shape, maybe we think it looks like a parabola, and maybe it does. So let's try to write our differential equation, or take our best guess at it. Well, we know it depends on x, and we know that it's 0 anytime x is equal to 2. So our guess might be something like x minus 2. Because when x is bigger than 2, it's positive. When x is less than 2, it's negative. And when x is 2, it's 0. So this would be our best guess. Now again, something that's particularly interesting about differential equations is that there's more than one answer here, right? We could have drawn this parabola or this parabola. And something that we've seen before in class is when you're starting with a derivative, to go backwards, we can always add a constant term, because a constant term's derivative is 0. So there are actually infinitely many functions whose derivatives are equal to x minus 2. For instance, 1/2 x squared minus 2x plus 7. Right? If this is our y, great. If I changed this plus 7 to plus 71, that's also a function that has this derivative here. So important to note that when we're dealing with differential equations, we get infinitely many answers. We can have tons and tons and tons of functions.